Welcome back. We are discussing in Fundamental of Electronics about the thyristors, its principle and applications. The overview of this lecture would be: first we will discuss the introduction to thyristors, the thyristor families and their types, the construction and operation of the thyristors, the key characteristic, what are the applications, the protection mechanism, and the conclusion. Thyristor is basically a semiconductor switching device which is having three or more PN junction. So we have studied the PN junction in case of a diode, and here the PN junction for this semiconductor device will be three or more. Why three or more? Because there are different families of thyristors which would have different PN junction, either three or more than that. It is basically operating in the bistable switch characteristic. So what is the meaning of bistable? So either the switch will be on or the switch will be off. It requires no continuous gate biasing to maintain the conduction. We will see that in this semiconductor PN junction, we will be having gate as one of the terminal, which would be required to on the thyristor, but it would not be having required to have continuous gate biasing. Generally, these thyristor operate for very high voltages greater than 1000 volt, and they are able to sustain the current very high, which is more than 1000 ampere. The word thyristor has been derived from the Greek letter thyra, which means door, and it symbolizes the current flow control. So the current which is flowing in the thyristor, we have to control it with the help of the gate signal. The different thyristor families are the Shockley diode, which is basically the PNPN diode, silicon controlled rectifier, which is SCR, and this is what is very famous, which we are going to discuss in very detail. The Triac, the full form is triode for alternating current, the Diac, which is diode for alternating current, the gate turn off thyristor, and light activated SCR. Please note, this is not only the full family of the thyristor. This is one of the few important families. There are other thyristor members also. SCR and triacs are basically widely used in the power control devices. So among the thyristor families, the silicon controlled rectifier and the Triac are wide famous in power control applications. Now, if we talk about the construction, the thyristors are basically 4-layer, so it can be 3 or more, and this form PNPN structure. So if you see here, the semiconductor devices are in the form of PNPN structure, and this is example of 4-layer diode. If you talk about the terminals, then among different thyristor families, whether it is a Shockley diode, SCR or Triac, they may have 2 or 3 or more terminals. So here the Shockley diode is basically having anode and cathode as the terminals. In SCR, you will have one more terminal, which is the gate, in addition to anode and cathode. The Triac will be having the terminals. The name would not be anode or cathode, but terminal 1, terminal 2, and the gate. So Triac is also having the gate as like SCR, but the terminals name is not given as anode or cathode rather than terminals A1 and A2. So this is the semiotic symbol of the Shockley diode, which is having 2 terminal anode and cathode. There is no gate. So when we talk about the Shockley diode, so previously we saw that diagram, which is a 4-layer PNPN diode. The other name is silicon unilateral switch. It is having 2 terminals, anode and cathode, and it would turn on when the forward voltage exceeds the breakover voltage. So when you apply the forward voltage in the thyristor, which is in the form of a Shockley diode, and if it is exceeding the breakover voltage, then only the thyristor will be turned on. It exhibits the latching behavior. Now, what is the meaning of latching behavior? Is basically the turning on of the thyristor and remain in the on state. This Shockley thyristor is in the form of a two transistor model, which is having two transistor Q1 and Q2, basically in the form of PNP and NPN transistor. So here we can see Q1 is basically PNP transistor, and the transistor Q2 is in the form of NPN transistor. The base of the transistor Q1 is connected to the collector of transistor Q2 and vice versa. So it means the base of transistor Q2 is connected to the collector of the transistor Q1. So both the transistors are connected in the same fashion so that it would provide the regenerative feedback for the latching phenomena. So here we are connecting external source, and there is a internal source resistance R, which is given the supply to transistor Q1, and both the transistors are connected in the form of regenerative feedback nature. So the working principle of this two transistor model is it is having high resistance in the off state, and there is a minimal leakage current would be flowing. But when the transistor is triggered on, if the forward voltage is exceeding the breakover voltage. So here we can see the characteristic where the x-axis represent the anode voltage, and here you have the anode current. So when the forward voltage is exceeding the breakover voltage, then the thyristor is basically turned on. So this is the turning on of the thyristor when the breakover voltage is exceeded. In this thyristor, whether it is a Shockley thyristor, you will not have the gate signal, but you will be requiring the gate pulse for the other thyristor families like SCR, Triac and GTO. In the on state, the resistance is low and the latch until the current drops below the holding current. So here you have two current, one is the holding current and another is the switching current. So if the current falls below the holding current, then the thyristor will be off, and thyristor has to maintain this minimum amount of the current to remain in the on state. So two transistors Q1 and Q2, which are the PNP and NPN type, are connected in between the base and the collector. Then the regenerative feedback connection is there, and if the voltage is exceeding this breakover voltage, thyristor will on. And so the operating regions, if we talk about the key characteristic, there is a region which is forward blocking, which is the off state. When the anode current is less than the switching current, it will offer the high resistance in the off state. Forward conduction would take place when the anode current is greater than the switching current. Transistor will be on and it would behave as low resistance in the on state. The transistor will be turned off when the anode current is less than the holding current, and it will return to the off state. So in terms of definition, we can say that the latching behavior means the transistors should stay on without the continuous gate signal. So even the gate signal is removed, then also the transistor is on. That is known as the latching behavior. The switching current is the current at which the device is turning on. So we require this current so that the transistor has to be on. Holding current is the minimum amount of the current to maintain the transistor on. So if the current falls below the holding current, then the transistor will be off. In the Thyristor family, the SCR and the Shockley diode are basically unidirectional device. That is, the current will flow in only one direction, whereas the Triac and the Diac are basically the bidirectional thyristors. So the current flow in both the direction. We will be requiring protection in terms of high di by dt, which is the current change with respect to time t, and the voltage change, which is dv by dt, rating critical for the performance. So these protection we required, otherwise the thyristor will burn out. So we have discussed the Shockley diode. Let us move to the SCRs, which are the silicon controlled rectifier having three terminals, anode, cathode and the gate. So you have anode and cathode, and there is one more terminal which is the gate terminal. So it is again the 4-layer PNPN semiconductor device which is having three terminals, anode, cathode and gate, and the thyristor will turn on via the gate pulse. So this gate signal, whatever we give, this will turn on the thyristor when the forward voltage exceeds the breakover voltage. The gate is triggering and it will control the switching characteristic of the thyristor even with the lower breakdown voltage. So, thyristor can be turned on easily at a lower voltage with the help of the gate signal. It is used in rectification and power control. The schematic symbol, if we see for this silicon control rectifier, is having three terminal anode, cathode, the gate signal, and this is the normal diode representation with the gate signal as extra as compared to the normal diode. Again, the silicon control rectifier equivalent circuit, which is the two transistor model Q1, Q2, and in along with that there is a gate which is the extra terminal connected. So if there is no gate, then it will behave like a Shockley diode. And with gate pulse, you can initiate the regenerative feedback and the silicon control rectifier will latch on and stays on even the gate is removed. So this gate signal is basically used only to turn on the thyristor. Once the gate thyristor is on, you can remove the gate signal and the thyristor will be keep on, which is known as the latching behavior. So if we discuss the equivalent circuit for the gate triggering and the on of the SCR, so initially if you see that there is no gate signal and the SCR is off, which is represented by open switch in case of the SCR. So no current is flowing in the anode. When the gate signal is given, SCR will be turned on and the switch will be represented with a closed one and the anode current will start flowing. If we remove the gate signal now, then also the SCR stays on and the anode current is flowing and hence we can represent this with the closed switch. So the gate signal is basically used only to turn on the SCR. In terms of the characteristic curve, if we talk about, then you can know that once the SCR is crossing this forward voltage, which is the breakover voltage, then the SCR is turned on and this zone is known as forward conduction region. So, and the minimum current that need to be maintained is the holding current, and then we can remove the gate signal. In the reverse bias, this is the reverse blocking region, and when the thyristor is not on, that is known as forward blocking region. So with the help of the gate signal, we can turn on the thyristor even with the less breakover voltage. So if you increase this gate current, then the thyristor will turn on with the less breakover voltage, and we can control the turning on of the thyristor with the help of gate signal. The thyristors or the SCR, one famous operation is basically the rectifiers, which is AC to DC conversion. This we have seen in case of normal diode, the phenomena of rectification. But here we can do the control rectification in using the SCR because of having the gate signal. So once the SCR, you are giving the triggering, the SCR will be turned on. And again, as we have discussed in normal rectifier, here in SCR rectifier, we have three types, which is half wave rectifier, full wave rectifier, and the bridge rectifier. And similar to the normal rectifier, which is the diode rectifiers, we will be having one SCR for half wave, two SCR for full wave, and in bridge rectifier, we will have two SCR and two diode without the center tap transformer. Full wave rectifier will require the center tap transformer. Half rectifier will control the positive half signal. So whatever the input you are giving, which is basically the AC input, the DC you are getting, whether it is half wave or full wave, depending upon what type of rectifiers you are using. So you can have the two rectifiers, SCR1, SCR2, to get the full wave and only one rectifier to get the half wave. This is connected in the form of a bridge. So it is known as bridge rectifier. You can have two thyristors and two diode for the rectification principle. So SCR rectifier waveform, if we see the half wave, the full wave, and the full wave in the form of a bridge rectifier. In the half wave, the conduction will take place from theta to 180 degrees. So this theta is basically controlled with the help of the gate signal, and hence it is known as the controlled rectifier. And it is in the positive cycle for the half wave. In the full wave of bridge rectifier, it is conducting in both the half cycles. So you can see here the negative half cycle for half wave is not there. So one half is lost in case of half wave rectifier, which is not present. In the full wave rectifier, both the half cycles of AC wave are rectified with a control operation with the theta, which is controlled with the help of the gate signal, and the average output voltage, which is given by Vm by pi 1 plus cos theta in case of the full wave. So if you do the derivation and try to find the average and the RMS output voltage for half wave rectifier, considering the input is sinusoidal wave, which is V equal to Vm sin omega t, and the conduction is theta to pi, average output voltage we can obtain as 1 by 2 pi, because the full cycle will be having 2 pi, and conduction will be from theta to pi, where theta is controlled with the help of the gate signal. So if we integrate the input, we get Vm by 2 pi 1 plus cos theta for the average output voltage. For RMS, that is the root mean square. So we are doing the root and the mean, and we have the square term here. So we get this value of the RMS voltage. So in the boundary condition, which are the special cases, considering theta 0, theta 90 degree, we can get the average voltage as Vm by pi and Vm by 2 pi. And in the special case of RMS, theta 0, we get Vrms is Vm by root 2. So this is what we generally know for the sinusoidal wave, that RMS voltage will be Vm by root 2. But here we will be having Vm by 2 for the half wave rectifier. In case of the full wave rectifier, whether it is in the form of the full wave or the bridge rectifier, if we find the average output voltage, considering again the input as V equal to Vm sin omega t, conduction taking from theta to pi in each half wave, and integrating from theta to pi, we get Vm by pi 1 plus cos theta. This is doubling the SCR half wave, and both the half cycles are utilized for the rectification principle. So efficiency will be more, and control output you will get by adjusting the firing angle. So this theta, which is the gate controlled firing angle, lead to the controlled rectification of these rectifiers, and hence it is known as controlled rectifiers. The other Thyristor families, the most famous one is the Triac, which is the triode for alternating current. So apart from SCR, the Triac is used for power control. These are basically bidirectional switching device. So SCR was unidirectional, Triac is bidirectional, and it is used for AC control. There are 3 terminals, the terminal A1, A2 and gate. Note here, we are not using anode and cathode. We are basically using the terminal name as A1, A2, and some books, they write MT1, MT2, means main terminal 1 or main terminal 2. This is equivalent to 2 SCRs in anti-parallel. So if you see the equivalent circuit, in SCR, we use only one diode representation. Here we use 2 diode representation, and they are connected in anti-parallel, and there is a gate signal. So it is a bidirectional device. The current will flow in both the direction. So it is triggered by positive or negative gate pulse. So you can see in the characteristic of the anode current and anode voltage, the forward and the reverse, both way the current will be flowing, controlling the gate signal. So this gate current in the forward and the reverse, both will control the direction of the current, and you will have control power by a phase control, which is the firing angle theta. So the terminals A1 and A2 and the gate together will lead to the Triac operation, which is bidirectional operation of the thyristors. So here again, this is basically 2 transistor model, where in the case here we will use 2 transistor for one diode and the 2 transistor for another diode. So totally 4 transistor operation will be there, Q1, Q2, Q3 and Q4. However, only 2 transistor will be on for each gate pulse. So it will remain off until the breakover voltage is reached. So we require to cross this breakover voltage to on the thyristor, which is in the form of a triac now. The leakage current will flow in the off state. Always the leakage current will be there when the thyristor is off. And in the conduction, it will pass the large current and require the external resistor to limit the surge. So here we are controlling this large current with the help of the external resistor. And in the positive half cycle, where the terminal A1 is greater than terminal A2, and in the negative half cycle, terminal 2 is greater than terminal 1. So you will be having the operation as bidirectional. So in the case where the thyristor or the terminal Q1 and Q2 both are on and other two transistors are off, Q3 and Q4 are off, then it is in the forward operation where the signal will be flowing in the positive direction. When Q3 and Q4 are on and Q1 and Q2 are off, then in case of this, the current will be flowing in the negative direction. So it will be triggered by both positive as well as negative gate pulse, which is not in the case of ACR. In the ACR, you have only positive gate pulse. So bidirectional operation is there, which is allowing a phase control, and the gate signal is adjusting the firing angle theta. So this theta is basically controlled with the help of the gate signal. So it is very efficient to control the AC power in the load when we talk about the bidirectional current flow. The other families of the thyristors, which is the Diac, is known as diode for alternating current. This is basically two terminal. So here you have A1 and A2 are the two terminals, and there is 3-layer bidirectional device. So you have 3 layers, which is you have 1, 2, and 3. And terminals A1 and A2 are interchangeable. So you can change these two terminals, but operation will remain the same. And it is not labeled as anode and cathode, similar to Triac, and it will trigger at breakover voltage. No gate control is required. So all the thyristor families, one thing is common in terms of operation, that you have to give a voltage which is triggering at the breakover voltage. This is commonly used to trigger the Triac in phase control. So Diac is used to trigger the Triacs. In off state, high resistance will be there until the breakover voltage is reached. Once the breakover voltage is exceeded, device will turn on and conduct. So this is the breakover voltage. Once you cross this, then only the conduction will start. And this conduction continues until the current falls below the holding current. So holding current is the minimum amount of current that is required. So Diac, like a Triac, it is basically bidirectional device where current will flow in both the positive and negative direction. The other family now is basically the gate turn off thyristor, which is a GTO. This is a powered semiconductor device that can be turned off using gate signal. So gate signal is used not only to turn on, but to turn off also. So that is the name it is given as GTO. These belong to the thyristor families and differ from SCR in turn-off capability. Remember, in SCR, the gate is used only to turn on the SCR, but here in GTO, the gate is also used to turn off the ACRs. It is used in motor drives, the traction, and the HVDC transmission lines. Here, the construction is again in the form of PNPN structure, where the 3 terminals are there: anode, cathode, and gate. So anode, cathode, and gate are there. Remember, this is similar to the silicon controlled rectifiers. However, the gate is used for both the turn on and turn off capabilities. The turn on means the positive gate pulse you are applying, turn off when you are applying a negative gate current. In terms of the equivalent circuit, how it is different from SCR is that in the gate connection, you can see here 2 lines will be drawn or arrow will be marked. Then this circuit will differ from the SCR. So it is again the 2 transistor model, which is the PNPN, NPN with the help of a gate, but gate is used not only for turn on, but for turn off also. So the working principle of GTO is, you can see here that it requires very fast gate drive for effective switching. So again, this characteristic which is crossing the breakover voltage so that the conduction take place and remain on till the holding current. So both forward and reverse blocking, you will have forward conduction, which is in the static mode. In the dynamic mode, it turn on in the time 1 to 2 microsecond and turn off 10 to 30 microsecond. That much time it will take. So gate will control the turn off and eliminate the need for commutation circuits. These we will discuss in detail in case of power electronics subject, commutation circuits, which is not a part of basic electronics here. So in case of silicon control rectifier, you required commutation circuit to turn off the thyristors. But in case of GTO, the gate itself is used for turning off the thyristor. So here we can have efficient switching for high power application, and we require to protect the dV by dt or di by dt. So one special circuit, which is known as the snubber circuit, is used to control and have the protection device. One more family we will discuss on SCR, although there are many families of SCR, which is light activated SCR. So light activated SCR is that type of SCR that is triggered by light instead of gate current. So we do not require the gate current, but we require the light. And it is similar, although to conventional SCR, but with the photosensitive window allowing light to penetrate the semiconductor layers. So here you can see that light is used on the SCR to triggered on, and there is no gate here. So it is known as the light activated SCR. So the working principle, we have the incident light, which is generating the electron hole pair, and these carrier trigger conduction, switching the device on. So instead of having the gate current, we are having the light. So the electron hole pair combination take place and the device turn on until the current drop below the holding current. So this remains the same for all SCR operation. So application wise, this is used for optical triggering for high voltage AC lines, the over voltage protection, the photonic switches in HVDC system. So the light activated SCR have got enormous application in many areas where we use the light as sensitive to semiconductors to turn it on. This is the entire comparison of various Thyristor family devices: SCR, Triac, Diac, GTO. There is another one, IGCT, which is integrated gate commutated thyristor. So we have LSCR, which is light activated SCR, silicon control switch. RCT means reverse conducting thyristor, MCT, MOS controlled thyristor. So there are different thyristor families. The most important one is basically the SCR and the Triac. So these two are very important, and in terms of the thyristor operation. So either you have the 3-layer or more, and you will be having the terminals, and depending upon these, you can have the switching either unidirectional or bidirectional, and different applications of these thyristors in rectifiers, dimmers, Triac operation, inverters, choppers, HVDC lines, logic circuit, induction heating, power switching. You can have different thyristors to operation. The turning off principle, which is the commutation, we say this commutation for different SCRs are different, whether you want the commutation as external or whether you want the commutation using the gate signal. So depending upon that, the application of thyristors will be different. In the previous lecture, we have seen about the field effect transistors, which is the power FETs. How it is different from thyristors if we compare it, then if we compare the features like switching, the thyristors may be bistable, either on or off, but the FETs are linear, on or off. It cannot be having both. So current rating is very high in case of thyristors, more than 1000 ampere, but in FETs, it is moderate to high. The control signal, we require the gate pulse in thyristors. In FETs, we require voltage controlled signal. Bidirectional features is available in thyristors and Triac, but in FETs, it is mostly unidirectional. Switching speed, if we talk about, then thyristors are slower, but FETs are faster. So different electronic applications, electronic devices will have different features. So FETs we have studied in the previous lecture. Here, thyristors we are discussing. Now we have seen that the thyristors, we required some protections. So the vulnerabilities, which is in the form of over voltage or over current, it is in the form of di by dt or dv by dt, which is high in terms of current rise or voltage rise. So it would cause the thyristor to turn on or have false triggering, which is not good enough. So we required some protection method. If we require di by dt protection, then we required the series inductor to be limiting the current. So we required some inductor which is put in series with the thyristor, and this will limit the current to the thyristor. dv by dt protection, some special circuit which is in the form of a snubber circuit, which is RC circuit, it's control the voltage rise. So when the thyristor, which is basically PNPN device, and you have three junctions formation with the junction J2 being reverse bias and junction J1 and J3 are forward biased, then in the off state, the leakage current will flow. But if you have this high current or high voltage, then the thyristor will turn on even the gate signal is not provided. So we need some protection for that. One circuit we used for dv by dt protection, which is called snubber circuit. Here the components which are used are resistors and capacitors which are in series. So these resistor RC, which is a series connected RC, it is connected in parallel to the thyristor. So it is a thyristor which is connected in parallel with the RC, and this circuit is known as the snubber circuit. This operation is the capacitor will limit the dv by dt by charging gradually, and the resistor will limit this discharge current when the thyristor is turned on. And hence the benefit is it will prevent the false triggering and control the di by dt. So snubber circuit is one of the most famous circuit for thyristor protection, both for di by dt and dv by dt. The basic construction is RC network connected in parallel with the thyristor. So the conclusion for this discussion is thyristors are robust semiconductor switching device and used for high power applications. There are different thyristor families. So SCR, Triac, Diac and JTO cater to the diverse need. Among these, SCR and Triac are the most famous. It enables the precise control in rectification principle, whether it is a switching application and in the power system. Its protection mechanism has to be ensured to reliability and longevity in the form of snubber circuit, and these are critical to modern power electronics for efficiency and control. So when we study the power electronic devices, we will see that the normal electronic devices are used in case of power electronics, which is electronics plus the micro electronics control features for the power electronic or high current, high voltage devices. So here we complete our discussion on thyristors. Previous lecture we discussed on the FETs. Now we will be moving forward our discussion in more deep for electronics. Stay connected. Thank you for now.